Hey everyone, welcome back to Bewitching Brain. We're so happy to have you with us and encourage you to subscribe and share. Take good care, be safe, and help others be safe. In the last video, Brett talked about the lateral corticospinal tract and how it allows for voluntary movement. Today we'll be talking about reflexes, which allow for involuntary movement. So to start thinking about reflexes, imagine that you're cooking in a kitchen with a hot pan. You're cutting up veggies next to the pan, and your hand accidentally touches it. Before you even realize what happened, your hand pulls away from the hot pan. This was a reflex. Reflexes allow for very rapid movement below the level of consciousness in order to prevent physical harm, such as a burn. In this video, we'll discuss the general reflex pathway as well as two main types of reflexes, and then we'll talk briefly about clinical reflex testing. So let's start by talking about the general neural pathway of reflexes. First, something happens in or to your body that requires reflexive movement. Let's continue with a hot pan scenario. The hot pan activates pain receptors in your skin. The pain signal then travels along a sensory neuron. This is called the afferent neuron of the reflex. The afferent neuron always travels towards the spinal cord. Its cell body is located in the DRG, or dorsal root ganglion. The sensory afferent then enters the dorsal horn of the spinal cord. Up to this point, the pathway has been the same as a general sensory pathway that we've talked about in previous videos. However, instead of going up the spinal cord, the signal actually short circuits at that spinal cord level, which allows for quick movement. The sensory afferent directly synapses with an alpha motor neuron. The alpha motor neuron is referred to as the efferent neuron because it goes away from the spinal cord. In the hot pan scenario, the sensory afferent activates the alpha motor neuron to produce muscle contraction, which allows you to pull away from the hot pan without even thinking about it. The next reflex that we'll be talking about is the muscle spindle reflex. This reflex responds to increased muscle stretch. When a muscle is stretched too much, this reflex responds by decreasing the stretch. The opposite of stretch is contraction. Therefore, the same muscle that stretched must contract. However, we also have to consider the antagonist muscle. So let's say that your biceps muscle is stretched too much. The reflex will activate the biceps to contract to counteract that stretch. However, if the triceps muscle, which is the antagonist to the biceps, did not simultaneously relax, the biceps couldn't effectively contract. Therefore, the muscle spindle reflex must activate the synergist and inhibit the antagonist muscles at the same time. So let's talk about the specifics of the pathway of the muscle spindle reflex. This reflex is pretty similar to the general pathway that we already talked about, with a couple different modifications. First of all, the muscle spindles in your muscles are going to sense increased muscle length or stretch. When a muscle is stretched, this activates the muscle spindles, which results in a signal traveling in a sensory afferent neuron. In the muscle spindle reflex, the sensory afferent is either a 1A or a 2 afferent. The afferent neuron then has two different jobs. One of its jobs is to activate the alpha motor neuron that goes to the synergist muscle, or the biceps in the example that we've been talking about. This results in contraction of that muscle. The other job of the sensory afferent is to inhibit the alpha motor neuron that goes to the antagonist muscle, or the triceps. To do this, it actually synapses on an interneuron within the spinal cord. An interneuron is a neuron that is contained only within the central nervous system. The interneuron connects the afferent sensory neuron to the alpha motor neuron. The interneuron in this image is purple, whereas the alpha motor neuron is blue. The interneuron inhibits the alpha motor neuron of the antagonist muscle, resulting in antagonist relaxation. To summarize, the muscle spindle reflex responds to muscle stretch by contracting the stretched muscle and relaxing its muscle antagonist. So let's talk about an important application of the muscle spindle reflex. So when a doctor or another medical professional uses their reflex hammer to tap just below your knee, they're eliciting the patellar reflex. By hitting the tendon below your knee, the doctor stretches the tendon and the quadriceps muscle, which is the muscle that tendon is connected to. This activates the muscle spindle reflex, resulting in quadriceps muscle contraction and your leg jerks outward. Similar reflexes are tested on your biceps and ankle. The ankle reflex is called the Achilles reflex. The last reflex that we'll be talking about is the Golgi tendon organ reflex. Golgi tendon organs, as the name implies, are in your tendons, and they sense increased muscle force. Here's an example of this reflex in action. Let's say that you've been steadily increasing your weightlifting for a few months. One day, you decide to increase your weight a little bit too much. And while you're lifting the weights above your head, your arms suddenly give out and you involuntarily drop the weights. This is a reflexive response to prevent too much contraction of your arm muscles. So let's talk a little bit about that reflex pathway. When a muscle has increased force, this activates Golgi tendon organs, which results in a signal traveling in a sensory afferent neuron. In the Golgi tendon organ reflex, the sensory afferent is a 1B afferent. The sensory afferent then synapses on an interneuron, which subsequently inhibits the alpha motor neuron acting on the same muscle that had too much tension. To summarize, the Golgi tendon organ reflex responds to too much muscle contraction by relaxing that same muscle. I hope this video helps you to understand reflexes a little bit better. Next time we'll be talking about ALS, or amyotrophic lateral sclerosis. Please join us. Once again, a huge thanks to Dr. Patitucci for her spinal cord illustrations. I'd also like to thank Tarini Mitra for her assistance in developing slides for this video. Thanks for listening, Brainiacs. Tune in next time for more.